So what I have for you guys today is overcurrent protection, some overcurrent protection device coordination. So that's kind of what I'm going to do this session, and then I believe Dave, we're here for 4 more meetings, right? That was the assumption. So we're going to be doing HVAC equipment and motor control and so forth. But today we're going to do overcurrent. So for the overcurrent, guys, what I did, the one-line diagram for the industrial project that I gave to you a couple of weeks ago, I put it in this Power Tools for Window. You guys are very familiar with Power Tools for Window. So how many of you guys use Power Tools for Windows? Just to give you an idea. Okay, so there's a bunch of guys and gals use Power Tools for Windows. So I put in Power Tools for Window, and I did some analysis on it, overcurrent protection device analysis. So I'm going to share this one with you. I printed a few things. I gave it to you. Should be very familiar to the people who use Power Tools for Window. So that's one thing I have with me. I do have also a couple of things here I want to show you. I have this is SPD, Selecting Protective Devices. I found it very interesting to have this PDF file. I'm sure a lot of you guys have it. A lot of coordination using fuses. A book like this you can have as a PDF file. So I think that comes very handy. And of course, we can't go anywhere without having an NDC code book with us. So 240, Article 240, that talks about the overcurrent protection device. But before I go ahead and start, guys, I'm going to go to my PowerPoint presentation, and then we'll go into. So my plan is to go over this 41 slide PowerPoint presentation. Please stop me at any time. And then I'm going to go to SKM PTW and go over a couple of things when it comes to the overcurrent protection device. So for those of you who are engineers or involved in higher than 600 volt, guys, you know that overcurrent protection is only one aspect that we protect our electrical power system from, right? We have also under over frequency, under over voltage, directional overcurrent protection devices, a bunch of other protections that we provide for any power system. So the overcurrent is only one of them. So I thought to focus on the fuses and the circuit breakers. I always like to bring this one, guys. I thought this summarizes the whole electrical construction, design, and maintenance. So we have the National Electric Code. That's our Bible when it comes to the construction of any power electrical system and design. And then we have oops, get that one here. So okay, here we go. And then we have our 70E, and that's the Bible when it comes to working on energized or non-energized electrical equipment. So I thought that when it comes to the overcurrent protection device and arc flash and the hazard, the shock hazard, and the arc flash, arc blast hazard, it's very interesting to know this document here, 2012, that has the procedures for working safely around and at energized electrical equipment. And then, of course, we have the white papers. I know the white book. I'm sure you guys have a lot of 212, the white book from UL. If you want to know what the difference between a switch gear and a switchboard, a panel board, a load center, 2012 from UL white book. You guys have a copy of it here? So they give it to you for free, the white book. It's really nice because it distinguishes between all different type of panels and switch gears, and what's the difference between power circuit breakers and insulated case circuit breakers and molded case circuit breakers, and what's the UL listing for them. So I thought I found it very interesting, the white book from 2012. I think 2013 is up and running for UL. So that's the safety of the equipment. It has to be a UL listed. Then we have safe equipment. We install and design it based on 2011. NEC code book. Then we work on it energized based on 70E so we can go home safe. We don't blow up our hands or electrocute ourselves. And then we have the, I don't know how many of you guys know the NFPA 70B. 70B, if you do any maintenance or you write a report for people to do maintenance, this is the Bible of maintaining any power system. And we all know, guys, the power system is as good as a maintenance program that you have it. So it talks about creating a electrical maintenance program, exactly like electrical safety program. When you work on electrical equipment, this is creating an electrical safety program. And then, of course, they have the authority having jurisdiction, which is OSHA enforcing all this construction and so forth. So I thought that's great to start with. Almost everything that you need to know in the NDC code book about the overcurrent protection devices in Article 240. The intention of the overcurrent protection devices is to protect the equipment as well as the conductors from excessive temperature, heat. So when we have a current going through a conductor or through a piece of equipment higher than what the equipment is rated for, you will create enough heat that will burn the equipment. So if you don't care about burning your equipment, 240 doesn't mean anything, right? So burning your equipment and excessive heat that will burn your equipment, and this is a good example of a switchboard that got blown up by an arc flash. So the whole idea of overcurrent protection device is protecting your equipment from being burned due to the high temperature or excessive high temperature. I thought I picked this one from this manual, SPD manual. This is how they test circuit breakers. So when they rate a circuit breaker, here's the distances based on UL that they test them, and they give him 14,000 interrupting rating. So just to give you an idea, UL and NEMA establish standards for rating of equipment. So when you have a switch gear and you say this switch gear is 85,000 amp interrupting as well as withstand rating, this is done, as we all know, by UL and NEMA, and they give them all these rating for the circuit breakers as well as for the equipment that houses the circuit breakers. A couple of things, guys, about fuses. So I don't know if you use a lot of fuses, disconnects versus circuit breakers. A lot of, at least my experience as an engineer, we like the circuit breakers because we can parallel with them and we can use them a lot. Though when you talk to people who work in the field, and a good protection, fuses have a lot of good advantages over circuit breakers when it comes to protecting electronic equipments. And so forth. So I thought just to start with the disconnect switches, with this will be a fuse disconnect switches. You can get them almost as high as 6,000 amps. I don't know if they go that high. Here you can go to circuit breakers at this level, and 250 up to 600 volt levels. Copper conductors, unless it's marked for aluminum. And this is what I want to highlight, is unless otherwise marked. Probably this is 110.14 is the most confusing one for the people when it comes to overcurrent protection devices and sizing conductor to land in an overcurrent protection device. Unless you know otherwise, if you have a piece of equipment that does not have any listing on the logs, unless you know otherwise, if you have a conductor that have an equipment that rated for 10 to 1 gauge 14 to 1, this equipment will be rated for 60 degrees Celsius. What does that mean? When you go to a 310.15b16 and you size your cable, if your equipment has 100 amp or less, also with it goes 100 amp or less, then you default to the 60-degree column. If your equipment is more than 100, which goes with a 1/0 and larger conductor, your equipment is defaulted to 75. That's the default unless you know otherwise. And my understanding, correct me, you guys are all engineers, this is coming from UL listing. So when you have the equipment 100 amp or less, it requires the equipment, more than 100 amp requires it to have lugs rated for 75. Less than 100 amp, it could have 75 or 60. So unless they tell you it's 75, the assumption is going to be it's 60. Who cares? When we size conductors, that becomes a decisive factor in terms of which column am I going to be going to. If you're dealing with three-phase equipment, almost always three-phase equipment's rated for 75, so you don't have to worry about that one. And also the disconnect we have a ground fault sensing. We'll talk about the ground fault protection. If you have a fuse disconnect, they will be able to have a sensor that sense if you have a ground fault condition and interrupt the system upon the existence of a ground fault condition. Any comments, guys? Any questions about these corrections? Please jump in, chime at any time. Like I said, I picked a couple of things from the article. Overcurrent protection devices, including fuse disconnect, must be readily accessible, with some exceptions. Occupants must have access to it. I don't know if you guys do apartment buildings. I don't think you do anything residential, do you? So if you have an apartment building and so forth, and you design a system, you have to give them access to their overcurrent protection devices, meaning the panel have to be in the apartment. The main could be downstairs somewhere, but the panel have to have the apartment have to have its own panels. So that becomes a big deal if you do apartment buildings in terms of readily accessible and occupants have access to the overcurrent protection devices. In terms of fuses and circuit breakers, there's a voltage rating and there's a continuous current rating. So this is summarizing it. You cannot put here 250 fuse shall be constructed so that it cannot be inserted into 600 volt. So when you have a fuse, the manufacturer they will make it in a way where you can't put a fuse rated for 25 volt, 250 volt into a system that's 600 volt. And also, at the same time, you can't put a fuse that rated for 60 amps in a fuse holder, special fuse holder that rated for 30 amps. Does that make sense? You don't want you don't want the fuse here to be larger than what the clip that rated for it, or the voltage also of the clip is, or the system is rated more than what the fuse can handle. So there's the voltage limitation and the current limitation, as you guys know. Any comments about the voltage limitation, current limitation on over? Same thing for circuit breakers applies, is voltage limitation and current limitation. Long story short, you cannot put a circuit breaker that's rated for 240 on a system that's 480. Or a circuit breaker that's rated for 20 amps on a circuit that's 15 amp circuit. Okay, any comments, guys? Any comments, questions? No? I didn't tell you that I have two speeds, one fast and one faster, and now it's going to be faster than faster because they have told me I have sharp cut off at 2:30. Okay, here's a rule that I don't like as an engineer. I'm sure you guys, but the contractors love it all the time when you go there. The 800 ceiling, there's a ceiling where if your piece of equipment, if you have an equipment 800 amp or less, your conductors can be slightly rated for lower than what the equipment is rated for. So for example, if I have a 200 amp panel, I can feed the 200 amp panel from a 500 kcm, knowing that a 500 kcm full load amp at 75 degree column is 380 amps. So long story short, you end up with a conductor that's slightly less amp-wise, continuous amp-wise, than what the conductor is rated for. As engineers, I don't like this one. Do you guys do? Or do you land a 500 kcm on a 400 amp? Contractors love it because it saves money, you know, and it works. And do you know why it works? Because most of the time our system is oversized anyway. So the load factor of any system that you do, like we talked last time, from 30 to 66, from 33 to 66, that's the load factor of any system. Meaning after you design the whole system, you're lucky if you can get 66% out of what you designed for anyway as a full load amp. Okay, so that's then this is another application where you can end up with an 800 amp with 2 runs of 500, give you 760. The 760 amp capacity of these conductors is slightly less than what the 800 amp, and that's okay with the NEC code book. That's fine. So if you see this one on systems, a lot of us go for 600 amp here, 600 amp instead of 500 amp, but that's okay, but just be aware of that one. Now you go to a 1200 amp switchboard or a panel board. Now you have to take you cannot use 3 runs of 500 because they're a little bit short of 1200 amp. Any comments, guys? Any questions about that? Any comments? Any questions? 80% of circuit breakers. That's a very good point. Unless you know.
Wait a second. A circuit breaker doesn't trip at 80% of its rating. That means that a circuit breaker could only handle 80% of its rating on a continuous basis.
So this.
It's still not going to trip. If you got a 800 amp breaker, if you put 800 amps on it and leave it there for the rest of the week, it's not going to trip. It's a code violation because the breaker will overheat, but it's still not going to trip. It'll hold 800. If you've got the high current curve, that breaker will hold 800 amps for a day. The code says that you can't apply a continuous current over 80% of the rating of that breaker unless it's fully rated. So, I'm sorry, but
It's a safety factor.
People say that imply that circuit breakers are going to trip at 80% of the rating if they don't.
Safety, it's a safety factor, like 25. Here's how it's really confusing, the 80%. Here's how I handle it. I always start with the load. Start with your load. Always, like when we did the load calculation, always start with your loads. When you get, so you have a continuous load, say you have a continuous load, and you know what a continuous load is, runs 100 amp or 3 hours or more, continuous load. So say you have a continuous load of 100 amp air handling unit. That's your load. Then you multiply this one by 125, 1.25, because we have to size the conductor, and that will give me what? That will give me 125 amp. That's the load that I have to size my conductor and my overcurrent protection device. Now then you take this value. Always if you start with the load, you don't get into trouble. That's my load. Then from here, you're going to go to the table to 240.4, 240.4, I'm sorry, dot 6, and that will tell you that 125, you just hit the jackpot. This is already a standard overcome detection device. Then you land your 125 circuit breaker of use here, right, as we know. And then you go from here to 310.16, 310.15, B16, B16. Anybody has what would that be? A number, whatever, number 2, say, and under 75. And then you will size your conductor for whatever the conductor would be based on the 125. That's, so you started with your load though, so you already accounted for the continuous load. But if you have a panel, the panel is 400 amp, and you want to know how much current you can pull continuously out of this 400 amp panel, it's 80% of that panel. But we as engineers, we always start with the load, right? Most of what we do is we start with the load. What's your load? And I size the panel for you. That's how I start. Okay, so that's your start point. And then when you put your when you put your conductor right here, you size your conductor. You came up with 500 kcm. Your overcome detection device can be slightly higher than, like we said, slightly higher than what the conductor is rated for. Now, if you land now from here, if this process here landed you in the 2000 amp, then the 1200 amp, then I start using the 1200 amp, not the actual load, to size my my conductor, You see the difference? So you're going to go, then now your load becomes your overcome detection device. Here's my overcome detection device that I size based on continuous load already, and then I divide it by 4 or 3, and I size my conductors. Any comments, guys, about the 80%? Any comments about the 80%? That's the confusing part. Like I said, a lot of us even don't like to do when we size the conductors. I don't know about you guys. We size the conductors based on 3 factors, and you choose the largest conductor. You have to be aware of that. Factor number 1, of course, if your load is continuous load, 1 times 0.25 times the load, size your branch circuit, service conductors, or feeders. Then you came up with size 1. Then size number 2, voltage drop. We have an issue with voltage drop on feeders and branch circuits. So you have to run a voltage drop calculation, especially on feeders, and size based on the based on voltage drop. Now that's size 2. Size 3 is bundling. What if somebody decided to put 2 feeders or 6 branch circuits in a conduit? Now you have bundling, right? You bundle them based on the temperature, and bundling all them in one conduit. You need to derate. So you might have to oversize your conductor based on derating. So these 3 factors that you size based on them, and whichever process gets you the larger conductor, you're supposed to use that larger conductor. So we came up with 500 kcm here. If we ran a voltage drop calculation, you might have to up this one into 600 anyway because of voltage drop calculation. Or if that was in an ambient temperature that other than the rated 30-degree rated ambient temperature Celsius, then you have to also up it because of the temperature. And I will do example like this one too. Any comments, guys? Any questions about that? Comments, questions? Always start with the load, and then size your conductor, size your overcome detection device. Yes. That's how I would do it. There's kind of a, you're absolutely right. So you size your overcome detection device, then you size your conductor. That's the proper way of doing it. Except there's a way that you can size directly based on the calculation here. If your overcome detection device is less than 800 amp, then your conductors. So for example, here's a good example. If my overcome detection device is less than 800 amp, then I can size directly based on the load multiplied by 1.25. The load, because when you, the next standard up. The next standard up. So 380, what's the next standard up from 380? 400. 400. The breaker. The next standard up. You can't go for 450 or 500 now. But that's only up to 800. After 800, you start match your cables to your overcome detection device. Absolutely.
Right. And if you looked at it recess load, you would look at that as the actual conductor capacity.
Yeah.
A number 500 is rated at 380 amps, but that's all I know.
The what? The 100 amp is rated for.
500, it's got a 75-degree rated capacity of 380 amps, so I don't think it's going to break.
Yep.
I don't look at it as a load, I look at it as
The wear size. Yeah. But if you, I hate to keep drilling on that one. If you want to know how much continuous load you can pull out of that 400 amp continuously, then you're going to take the 400, multiply it by 0.8. That will give you 320. So actually, that system is rated for 320 amps actual continuous load. Actual continuous load. But how often do you? That's what. If you want actual continuous load. Even though the conductor can get you 380 and the circuit breaker is rated for 400, but continuous load is rated for 320, unless it's 100% rated circuit breaker, which they use in the power circuit breaker as well. Okay, so that one. The other thing is, when it comes to circuit breakers, there's three very important values for circuit breakers. The most important one is, of course, the full load amp, the continuous load rating. That's or the 80% of the continuous load. That's the full load amp rating of that circuit breaker. The second one is the interrupting rating. This is the highest current that the circuit breaker can interrupt with minimum damage to the equipment, based on the rating. So that's how much current the circuit breaker can physically, mechanically interrupt, heat and magnetic wise. Then there's the short circuit. So that's for the circuit breaker. There's a short circuit current rating, or they call it withstand rating. This is if you have a panel 400 amp rated, withstand rating of a panel. That's when you have a short circuit inside the panel. This is how much the short circuit withstand rating, how much it's withstand in terms of shaking. I call it shaking and baking. When you have a short circuit condition inside the panel, you're shaking the panel from the magnetic force, and you're baking it from the heat generated in this panel. So how much that panel can handle being shaken and baken, or shaking and baking that panel, that's called the withstand rating. So that's the withstand rating for equipment. Interrupting rating is for circuit breakers. And typically, if you have a 4,000 amp switchgear, and it's an 85,000 interrupting rating, that interrupting rating of the circuit breaker and the withstanding of the equipment is typically the same. And then the speed of response for the overcome detection device. The speed of response for the overcome detection device will be the decisive factor of how much arc flash, arc blast, and damage to your equipment is going to encounter upon the existence of a ground fault or short circuit. How fast your circuit breaker is going to turn. Is it fast acting fuse? Is it time delay fuse? And I have a couple of that's where the whole coordination becomes a well coordinated system versus a not well coordinated system in terms of safety and in terms of survivability of the system. Any comments, guys, about the interrupting rating, the withstand rating, and the speed of response for the circuit breakers or fuses? So we have a couple of things, guys, about dual element time delay fuses. I'm not a fuse guy. I don't know. Do you guys do a lot of switch gears, Dave, here? A lot of fuse, disconnect switch gears? Circuit breakers, yeah. The more I teach and I train for contractors, the more I almost change my mind to fuses. I really do. So the people who maintain the system, they'll tell you, if a fuse blows up, I know it blows up. I know it worked. If a circuit breaker sits inside your building, it sits for 2 or 3 years, if it's not properly maintained, you really have no idea if that circuit breaker will trip, not just trip and act exactly how it's supposed to be. Now that's where 70B becomes a big deal. When we design a 4,000 amp switchgear, 85 interrupting rating, withstand rating for a switchgear, that's one assumption, assuming that this equipment will be maintained properly for the life of the equipment. If the equipment is not properly maintained for the life of the equipment, then that switchgear that you put with 85,000 interrupting rating, over time, the interrupting rating might go down to 86. 85 will go down to 70 or so. So unless you maintain it properly, and that's where maintaining the power system properly becomes a big deal. Fortunately, or unfortunately, we as an engineers walk into the building, we design and we move out, right? Typically, you guys do maintenance on the system so we don't maintain the system, but in the back of your mind, you're going to think of designing a system that's going to live 50 years from now, properly maintained. It should act exactly how you design it for. So I thought that's so dual element time delay fuses, a good application for motors. We'll talk about motors, guys. I mean, next meeting we're going to be talking about motors. And it provides overload range, unnecessary opening of circuit breakers because of harmless overload, and also it provides an overload protection as a backup. So what they do with these dual element time delay fuses, one element, as you know, is rated to give you backup. You can be using it as a backup for overload protection. And I'm not going to talk about overload versus overcurrent because we're coming on Thursday. That's going to be the topic for motors. But these fuses will provide you a good dual element. It will provide you unnecessary tripping because it has a delay, intentional delay on it, and a backup overload protection. The other one is the high starting currents of motors. Nuisance tripping and time characteristic curves. So this is just a few things of application of these fuses. When you have the intentional delay of the fuse, will prevent you from nuisance tripping on the customers. And of course, you have to have the current curves, which we will be talking about in a second here, to make sure that they will handle the momentarily motor start inrush. So it will be seen much better when we go into the curves. I'll show you where the inrush we have a starting curve for every motor, and you guys have power tools for window. No, there is no reason not to go every time to have a motor. You go check how is this sitting of this circuit breaker instantaneous or fixed, will make the circuit breaker start and clear the inrush of that circuit breaker. I'll talk about this one a little bit more when we talk about motors. This is just a setting of dual element time delay fuses. If you have a motor 100 amp, say 100 amp motor, just to make it easy, call it 100 amp. You can 100 times 1.75 give you 175 amp dual element time delay fuse. Stick it in there. That will provide you short circuit ground fault as well as a backup for your overload protection. A backup overload. This guy is rated to 5 times. 5 times typically can handle currents at 5 times larger than what the full rating is, and for only 10 seconds. So if the motor is 100 amp, it will handle 500 amps for 10 seconds. So what would that be? That's your starting current on the motor. So for 10 seconds, what happened after 10 seconds? If you go 11 seconds, this will be seen as a ground fault or short circuit, and bam, it will severe and open the dual element time delay fuse. This is rated for 5 times. The fuse is rated for 5 times. Again, when you do the coordination, you guys have SKM power tools for window. If you were to put a fuse the way I would do it, yeah, up. You're absolutely right. So the lower the amps, the more it will handle it. And the higher the amps, inversely proportional. Inversely, we'll see that on the curve that we do. There's a couple of effect acting and current limiting fuses. These are used on the feeders. I thought just to throw them. If you guys use fuses, this is an awesome guide for which fuse should be used where in application. But dual element, typically motors, fast acting feeders, extremely fast. What's the advantage of extremely fast? When it comes to your arc gas study that you did, it will reduce the amount of energy, incident energy that the system will produce substantially lower, which in turn lowers the PPE gear that the maintenance guy is supposed to put on when they work on these equipments. The lit through energy it will be much lower because it has the lowest energy lit through, lower energy lit through, which means less arc flash, less arc glass out of the system. You kill less people if they work on it energized. And here's a couple of applications where you can use it: main feeders, sub feeders, and so forth. So that would be a feeders like panels and so forth. Okay, types of cartridge fuses. This is just a couple of things directly from the code. When you have a cartridge fuses or any of these, they rate them based on amps, the full load amps of these equipment, then the voltages, then the interrupting rating. The assumption is they're all 10K unless if it's not labeled, it's 10K. Other than that, they have to be labeled. If their current limiting is a big deal, current limit fuses, we'll talk about this in a second, and the trademark and the name of manufacturer so we can sue them if something happens. So these are required by the NEC code book to be labeled on your overcompetition devices, mainly the fuses. Okay, so I picked these, a few things about fuses, knowing that you probably wouldn't use a whole lot of fuses. There's something called cable limiters. Do you guys use cable limiters with your parallel switch gears? Cable limiters. So the cable limiters, if you have 11 runs of 500 to carry a 4,000 amp switch gear load, so typically used with parallel cables. Utilities love them all the time because it's survivability of the system. So what they do is they isolate the faulted current and select it on the basis of conductor size and ampacity to protect that particular conductor. Cable to cable, cable to busway. So here's what they do. I have an 800 amp. It looks like we have a system, a power system here. 800 amp fuse, it looks like, and we have 3 sets. So what they do, in addition to the circuit breakers that you have and the fuses, you can see that there are fuses and circuit breaker and fuse disconnect or circuit breaker here. In addition to this protection, what they do in each run, they put this limiter. What this happen if this run is to have a ground fault or short circuit in that particular conduit run, what would happen if you don't have the current limiters? It will shut down the whole system. Now the current limiter will look, if one of these runs is faulted, it will interrupt that particular run. Now the question would be, what happened then? Aren't you going to overload the other, right? That's the first thing that would happen is if the load is supposed to be carried by 3 sets and you interrupted 1 set, what's going to happen to the other 2 sets will carry the load. Now, knowing that the load factor will be, like I said, from 33 to 66 of any power system, this will cover a lot of applications for you. It will contribute to the survivability of your power system, basically. There will be a situation where if one of them is to trip, it could overwhelm the other 2 sets and it will overload them and they will trip. But that will be, if I dare to guess, probably 20% of the time. 80% of the time, if one set is to trip, the load will shift to the other sets. You isolate that part and you work on it. And who cares? Your system continue to operate. The survivability of your system. Utilities use them all the time also too because they're not considered. They don't care much about protecting equipment. So what they do, they go to the secondary of the transformer and feed multiple buildings from it, and then if one of these they isolate that particular building from the power system. Isolate that particular building, and the other buildings will continue to operate. Anybody, you guys use them in paralleling? Dave, do you don't put them in paralleling? It's more utility type. I've never used it too, but it's really nice to be aware of that one. I don't know if you guys use a grounded system, a corner grounded system. Rarely, if ever. So when we talked about grounding, as we talked about last time, we said you can run, I would say 90% of the time, 95, you're running a solidly grounded system. Then there's a time when you run ungrounded system for the survivability of the system, or impedance grounded, which is the mixture in between. Grounded system, if you have, and don't forget that there is a leg coming from here that's not shown, coming all the way to here. So if you have a system like this, then you can see that phase B has to be grounded. The reason why I put this one here is because if you have an overcompetition device, you cannot put a fuse. This is basically a cover bar that they put there, because you cannot individually fuse a grounded circuit breaker. Even though this guy is phase B here, it is a grounded conductor, as you can see right here, so I cannot individually fuse. I can circuit breaker them all because it trips them all at the same time, but individually I can't fuse a grounded circuit breaker, so you end up putting that little bar here, which will, it looks like a fuse, but it's really a copper bar. that you stick it in here in a place of a fuse. Any comments? So that's the reason why I picked this one, because kind of unique a little bit, unique application. The grounding system. So I thought just to, this is at the main. Now if you go down at the level of the overcome protection device for motors, which we will talk about tomorrow, if you're using the fuse, one fuse, dual function, overcurrent protection device, ground fault and short circuit, as well as overload, doing dual function in one device, not as a backup, dual function, which we allowed by code, then you have to fuse it. Now this fuse that we put right here is actually not an overcome protection device anymore. It's an overload protection device, because there is no overload protection downstream here. So that's an exception where the code allows you to put a fuse in it. I thought that's a unique application for the overcome protection device. Okay, moving into the circuit breaker. Define the circuit breaker, guys, in the NEC code book, and the types of the circuit breakers. It's basically a circuit breaker, a device that can manually open and close. A switch, act like a switch, right? You walk into a circuit breaker, turn it on and off. That's the advantage of it. You can't do that one to a fuse. Unplug and unplug it loaded. That's number one. And number two, of course, it will trip under predetermined condition. It will automatically trip under predetermined overcurrent condition. So if you have an overcurrent condition, higher current than what the equipment is rated for, it will trip inversely proportional to the time. Inversely proportional to the time. Okay, a couple of things, guys, about circuit breakers, and you are very familiar with them. I thought this is, you're looking right here at the top at a power circuit breaker. That's the top-notch power draw-out circuit breakers. We use it for, it makes sense at 1,000 amp or higher, you start using it. And then the rest of them, a lot of us will use molded case circuit breakers. I believe molded case circuit breakers can go up to 1,200 amp. Anybody correct me if I'm wrong here. At voltage is 600 volt. And 250 and 480 and so forth, 1,200 amp. And then after that 1,200 amp, if you need 6,000 amp, which is rarely used, then you have to go to where? 6,000 amp, you have to go. Molded case circuit breakers, what they do is they mold them all together. You've seen them, it looks exactly like this one. And they can be electronic circuit breaker, or they can be thermomagnetic circuit breakers. It doesn't matter. Molded case is just how they build them. So when you go to the power circuit breakers, they build them completely different. So it's a device that you can unplug, put on the table, and work on it, as we all know. Then the insulated circuit breakers, and I believe Square D does that, and a bunch of them. It's kind of a hybrid between the power circuit breakers, right, and the molded circuit breakers. That's my understanding. It's cheaper than power, and one step higher than the molded case circuit breakers. And it has to do with UL listing. If you have a power circuit breaker, is listed under UL. I can't remember what the number is, but if it's molded case or insulated, it has a completely different UL listing. So top-notch, the Cadillac type circuit breaker is a power circuit breakers in terms of the equipment. A couple of things, guys, I thought just to grab this one directly from the NEC code, these articles. Main circuit breaker that has a higher interrupting rating while making the assumption that the branch circuits are protected adequately against a short circuit. So this is where it becomes series rated when you series rate the panels. Assuming if your main has a higher, very high interrupting rating, your branch circuit is also rated for this. That's a bad assumption. When you have a panel, you have to be looking at two things. Number one, the interrupting rating of your main, either inside the panel or upstream, and number two, the interrupting rating of your branch circuits. And that will lead us into series rated versus fully rated circuit breakers in a second here. Standard molded case circuit breakers with high interrupting rating cannot protect standard end use equipment having lower interrupting rating. This is the difference between interrupting rating and withstand rating. You have a good example because of this. You have a PLCs, electronic equipment, VFDs. You put your circuit breaker there thinking that your circuit breaker will interrupt the short circuit, but will the VFD handle the short circuit inside it enough for the circuit breaker to interrupt it safely, or would it burn? So that's the whole idea. So the circuit breaker will trip, but not before your VFD or soft drive or whatever burns. So that's where it becomes fuses and current limit fuse becomes a very an advantage. Where every time you have a soft start, electronic equipment they call them power electronics, like soft start VFDs in the system. Fuses become an advantage, and sometimes the manufacturers actually fuse them at a certain value to protect them. So that's be aware every time you have a power electronics in the circuit. Make sure that they have either withstand rating by themselves or with in conjunction with a fuse. That will lead us to the series rated. I'm sure you guys a lot of you have seen series rated equipment. The reason why we use the series rated equipment, and I remember Jerry Stanson from Square D and all those guys, they come here, right? And Cutler Hammer guys, Todd Christensen, they love to talk about these series rated. The reason why we do a series rated because we want to save money. So instead of having, here's a good example. Where would a good application you guys use series rated? Very simple. A great application if you have a lighting panel or a receptacle panel. Anybody can think, do you guys think of any other panels, if you have a bigger building, that series rated equipment would be a good application? You wouldn't put them on a mechanical equipment panel if you have a mechanical equipment panel. You can't anyway, even if you want to. So if you have a series rated panel, if in a building, is mostly used in receptacle panels as well as lighting panel. Why? Because receptacle panels and lighting panel do not contribute to the short circuit. If there's a short circuit in this panel, it would not kick back a short circuit current into the panel to add to the existing short circuit in it. Okay, so cost is a major thing here. That's why we love them. So if you have a 225 amp lighting panel, and all your circuit breakers are 20 amp circuit breakers and typically 20 or 30 amp circuit breakers, lighting or receptacle circuit breakers, that's a great application for it. So what does it mean? It means the main right here has a higher interrupting rating, as you can see, than the actual branch circuits. So if you have a branch circuit right in this area here, these two circuit breakers by manufacturer or under engineering supervision will be coordinated. So if the short circuit downstream is within the capability of the 20 amp circuit breakers, meaning 10 or less, the 10 will open. If it's higher than that, 20 amp circuit breakers, 10,000 amp interrupting rating will stop and hold until the big boy will take care of it. So do you guys use them all the time? No? Do you use fully? On the branch circuits, receptacles, and lighting. So I thought that's a good example of having interrupting rating. So if there's a short circuit on the line side of the branch circuits, right in here, right, which one do you think will see it and trip? The main will see it. We're only concerned about the load side of the circuit breaker. In the line side of the circuit breaker, the main 22 amp will trip and interrupt it. Any comments, guys, about the this is called series rated equipment, receptacle panels, lighting panels, the main gear for it. Now, if you have a series rated panel, the code require you in terms of labeling to throw a couple of labels like this: engineering series combination system rated, the amps, identified replacement component required. If you have a QO circuit breaker, you cannot put a QP if they are series rated. So you have to use, unless it's identified by the manufacturer. So you have to use, when they are series rated, if you series rated circuit breaker A with circuit breaker B, you can put C instead of A or B. So as you all know, SPD guys have tons of which fuse goes which fuse to get your circuit rated. And as a matter of fact, they have fuse to circuit breaker series rating. So this is under engineering supervision. If you're a registered engineer, you have the capability of in the field doing them. There's also series combination system rated. The amps, identified replacement is required. This is if it's tested in the factory as series and labeled as series rated. Label for existing, and this is for existing also under engineering supervision. Any one of you as an engineer can walk in and label the system rated this amount, replacement with this type of circuit breaker, and this type of fuse if needed. So the point is, if you have a series rated system, you must have a label similar to this one to identify it's series rated, and it's what's the replacement for what type of replacement do you need. Any comments, guys, about series rated equipment? Great, because they're cheaper. There's a sheet I didn't copy it here comparing 22,000 amp interrupting rating circuit breaker compared to a 10,000 amp, and you can see the difference is substantial. 2 times, sometimes 3 times more expensive. The same circuit breaker with higher interrupting.
Yeah, comment, we're not going to be pursuing the engineered series combinations in any projects that I
It's liability. A lot of liability.
That's a policy statement.
Yeah, that's a liability. Absolutely. Yeah. The same thing on
Same thing with the fuse went through.
Yeah.
Current limiting fuses has been proven by plant reviewers that one of the reasons we don't use fuses is because we can never prove
Yeah.
to any plant reviewer what the actual lesson is. They won't allow the use of the graphical method in any plant reviewers. So
Yeah.
that's what this considered.
And that, yeah, absolutely. I got approached a couple of times by people to evaluate equipment that's not even listed, and being a PA engineer, I can, any one of us PA, but would you stick your head on a piece of equipment coming in from India and say, yep, this is equivalent to 85,000 amp, and I do have a voltmeter in my basement that I can measure with. So it's, yeah, it's liability issues. There are engineers who do that though. There are engineers registered with the state that they can do all this.
Well, but that is plants do it all the time.
Yeah.
In an industrial setting.
Yeah. But on the other hand, looking at the industrial settings, as they want to protect very, very equipment. I do training at Gurdu. Gurdu is they're one of the largest. They do steel here, and if you walk into their plants, those guys have very, very expensive equipment, PLCs and VFDs driven, and a circuit breaker wouldn't cut it there to protect their equipment. They will burn their equipment, so they really have to use the circuit breaker as a protection for the feeders coming to the MCC or to their control panel, and there they fuse them properly to protect the equipment. And there's nothing wrong with that, using the circuit breakers as a feeder protector, and then downstream you go and you fuse to protect the equipment themselves. There's nothing wrong with that. Supplemental protection. Fully rated equipment. This is mainly used if you're feeding any rotating machines, any machines that can kick back short circuit. So if you have an air handling unit, rooftop unit, chillers, and so forth, your system have to be fully rated. And a good example of this one, the main panels in a bigger building, as well as mechanical panels, equipment, owner equipment panels if you have manufacturing floor, and so forth. Okay, so that's this one. Here's a couple of things. If you have series rated, there is the NEC code book require you here. I don't know if you guys, I'm sure you paid attention to it. Sets for 2 requirements to use a series rated. Number 1, do not connect any electrical motors between the load side of the higher rated overcam protection device and the line side of the lower rated devices. So you basically, you cannot connect. If going back into this, here's the load side here, and here's the line side here. I can't take another circuit breaker here, and here's my air handling unit here. Put my air handling unit now. I can't do that. Motor. So that's requirement number 1. There's an exception though. The sum of the connected motor full load current shall not exceed 1% of the interrupting rating of the lower rated circuit breaker. So that will allow you, if you have a smaller strip mall and so forth, and there's a couple of fans, smaller fan, that allow you to use a smaller fans on a series rated panel. That exception here, very small equipment. So the sum of the connected motor full load current shall not exceed 1% of the interrupting rating of the lower rated circuit breaker, So so that's a couple of exceptions to use that one. Okay, motor, this is just talk about if you're using this one. We'll talk about this one again, guys, on motors. If you're using inverse type circuit breakers, your multiplier for motors is 250. If you have instantaneous strip like motor protector, you can go as high as 800%, or if it's designed be efficient, you can go 1100%. So just imagine if your motor is 100 amp, your circuit breaker will be 250 rated. if your motor is 100 amp, your circuit breaker, instantaneous strip circuit breaker will be 800. And we're not talking about 250, it will be that big. The 800 amp is not going to be that big. These are specially designed circuit breakers. Size-wise, they are not that big, the instantaneous strip, but they don't have the overload component. They only have the instantaneous. So it used to confuse me later on. I don't know if it confused anybody. When instantaneous strip circuit breaker 800, you think it's that 800. You know, it's this is not the full load amp rating of that circuit breaker. Engineering supervision. This is where you guys exercise your judgment, because you're willing to go to court for it. Sometimes you can exceed all these values. You can see how much you can exceed it. Can demonstrate the need to exceed, but you have to have a need to exceed it. I've been in a project, guys, when after you do it, you size based on the code and circuit breaker trips because of rush. You can, as an engineer, you can exceed it. Here's a couple of values that you can use to exceed these, what the code is asking for. Okay, this one is about HVAC equipment. And we'll talk about HVAC equipment, guys. HVAC equipment has to have labeled by either maximum fuse and circuit breaker, maximum fuse or hacker circuit breaker. So that's when you get into your circuit breaker. If it's used in any piece of equipment that has compressor in it, refrigeration, anything that has a compressor in it, it has to be either, if it says fuse, you give him fuse. If it says circuit breaker, give him circuit breaker. If it says fuse or circuit breaker, then it doesn't matter. So how do we solve the problem? If you have, here's a good example. If your panel is, so this one here, it says maximum size fuse 40 amps. So what they want you to protect the equipment, they want you to put a fuse. But I have one little problem here. I only have a circuit breaker panel right in here. So what am I going to, how are you going to modify a circuit breaker panel to put a fuse? No problem. You size the circuit breaker here to protect your branch circuit here. And then right next to the equipment, you are required to put a disconnect anywhere to isolate the system to work on it safely. You go stick a fuse rated inside. Instead of non-fuse disconnect, it becomes a fuse disconnect rated based on what they want you to do. So the circuit breaker becomes nothing but protecting your equipment. I thought to throw a couple of short circuit calculation by hand because you guys like to do that. The ones who don't have access to SKM. Here's a couple of examples of short circuit calculations, and I think you have that one. You should. This should be part of the PowerPoint presentation too. Still, so here's an example of finding the F factor, and I'm not going to go through all this one. I thought that's a really good example. I always show it to the contractors who don't have SKM if they want to do something by hand to be dangerous. So you, based on the impedance. What we do is first for the transformer, like you guys know, first to find the full load current of a transformer, take the kVA of that particular transformer divided by the voltage, the 1.73 component for the 3-phase, and then you divide it by that value by the impedance of the transformer. That will get you the multiplier, and then you multiply the multiplier by the full load current, and that will give you the available short circuit current right at the terminals of that transformer. And then if you have motors, here's what I like. If you're, I don't spend too much time on it. If you're doing motors, then you multiply 4 times the full load current of your motor or motors. That will give you the contribution of your motors to the short circuit inside your building. That coming from contribution of motor. 4 is an assumption coming from that book here. These are based on the SPD. You, by any means, you can use 5 and select the inrush, the balance between 4 to 6% inrush of a motor. Then you add them up, and that will be the contribution of motors as well as the electrical utilities, infinite source. They call it infinite source contribution to your power system. And then, so up to this point, that's just the available short circuit at the terminal, at X1, right here. This is at the terminal of the transformer, right in here. Now, when you pull conductors, guys, to the fuse disconnect, so you go to X2, then you have the F factor, and these are all formulas that you can plug them in. The most important thing is the component. This is contribution. This one here and this one. These are 6 runs of. I don't know if you can see. I have 25 feet here of 6 runs of steel. service interest of 500. So I have 225 feet of 500 kcm, 6 per phase. The contribution, the impedance contribution that's going to knock down the power system is coming from this formula. Then you get the M factor, then you knock it down by 0.9 basically. So now, because of the impedance of the transformer and the impedance of the cable, I knock down my short circuits right at this point from 58.7. Well, you still have to add, and then you add the contribution, of course, of the motor right here. After you add the contribution and knock down the service, it knocks it down from 50, almost 58.7 into 57.0. So that's doing calculation by hand, short circuit calculation by hand. The most it's cumbersome, you guys probably doesn't, it's really nice for us as an engineers to go through it just to verify, because we don't see the math behind all the SKM. It's really nice. You hit comprehensive calculation, it gives you all the calculation for it, right? You don't have to worry about this one. Then you go to X2 here. So now you moved another, see, this is 2 points, calculation at 2 points. Here's I have a 400 amp. I moved, here's what I moved. I moved another one set to 500 feet kcm, and I need to contribute to it. So here you go. Here's a 500. This is multiplied by 1 because only one set of them. Knocks it down again after you add the contribution of the motor. Look at that. We knock it down to 42. My point is, guys, from the point, here's 25 plus 50, 75. 75 feet away from the transformer. 75 feet away from the transformer. You knock down the short circuit 3-phase from 58.7 to 42.66 because of the impedance of the cables. So I thought this is really good, good example. I always call it the happy medium. Every time you have equipment closer to the service, you have the advantage of low voltage drop problem, and the disadvantage of what? High short circuit rating. So that's kind of the nice thing about having your equipment closer to the surface is you have a low voltage drop calculation, like I said, but what's the disadvantage is your short circuit become higher. You might have to go to a higher rated equipment because of that. Here's a short circuit for single phase. It's not just, I don't think you guys do 3-phase. Now that multiplier for cables is coming from here, guys. The impedance is based on, here's what the impedance is based on a couple of the conductors, for example. So if you have, I think, what was it, 25 feet here? What was this? I can't remember if the system 480. We have 25 feet at 480 system, and I had 500 kcm and 6 sets of 500 kcm or 2 sets to 500 kcm. So it gives you the impedance of the cable anyway. I don't want to, so that will give you the impedance of the cable to do the calculation right in here. That number at the bottom here is the impedance of your cable, the impedance or contribution to the impedance cable. So if you don't have the software, that's what you're supposed to go get that sheet. All these sheets that are available right here in this book, that's available free. If you want to really look at it online, there's a PDF file of it. So that's okay. So that's the short circuit at different distances from the transformer. I'm sorry, I'll let you. The 500. Here's the 500 that we stuck in the example. 500. Right here. You guys 2218. That's the impedance of the cable that you use. They call it the C factor for 500. And you just stick it into that formula. This one is giving you the short circuit. These are actually short circuit. My apology. These are short circuit at different values away from a special transformer, which is 300 kVA transformer, 3-phase, 2 impedances. They're giving us a table. Right, if you look at 0, when it's 0, meaning right at the terminal of the transformer, if you're using 2 sets of 3/0 here. And if you go, say, 50 feet, 60 feet, if you go 60 feet away, it knocks it down to, what is it, 11.72 from 37.8. So this is calculation have done for one particular transformer commonly used. I apologize. This is the actual calculation. These are values are short circuit, already done, tabulated for us. Well, who cares? We already have a scam, right? So this is the one that you find the impedance to put the C factor in. Okay, so this is just a couple of calculation where you find the short circuit. right here at the terminal of your transformer, 34.7, 31.3, then your equipment have to be rated for 35, 34.7 or higher, your overcome protection device equipment. I thought as long as we're doing a short circuit, one of the advantages of having a short circuit, guys, is the arc flash, gun. Okay, so there you go. So when we do the short circuit calculation, if you're lucky, I always say if you're lucky, you have a bolted short circuit, meaning you take phase A, phase B, phase A, B, and C, you bolt them together literally with a piece of copper, and you flip the switch. That will give you the highest amount of current, no arcing, no sparking, and the circuit breaker will immediately trip if it's sized appropriately. Now, if you're not lucky, you drop something inside your switchgear and you have a high impedance short or a ground fault. That's the unlucky one. Now, if you have a high impedance short or ground fault, it's going to sit there instead of tripping because there's an impedance in it high enough to prevent the circuit breaker from tripping fast and low enough to create arc and spark inside your equipment and burn your equipment. That's where you get yourself into the arcing faults. So here's the component. These are, if you have LL, you guys are familiar with LLL if you use SKM. LL, line to line to line. You have phase A, phase B, phase C tied together, flip the switch. If your system is 480, so you take your bolted short circuit, 3-phase, 89% of it will be the contribution to calculate the arc flash. Now I always bring to your attention, look if your voltage system is 208, how substantially the arc of a 208 system is substantially small than the arc of a 480 system. A 480 system, can you see 12% only of a voltage short circuit in a 28120 will contribute to the arc flash. Who cares? If you have a 28120 panel, the PPE requirement on these panels will be very relaxed, basically. It doesn't have to go all the way to 4. You can get away with the PPE 1, which makes people more comfortable as they work on these electrical equipment. So here's a couple of categories I thought, just because this is directly related to the arc flash, overcurrent protection device, arc flash. So I got category 0, look at the, so you're comfortably, and by the way, they're not that fat. I stretched them this way. They look like really fat, these guys. They're not that fat. I should have stretched it the other way. You're going to think all electricians are really big. Shouldn't have stretched them. So category 0. And category 1, and it goes all the way. The last thing you want to do is you put somebody on a summer to work on a piece of a switch gear like in category 4. That's 40 calories per centimeter, and that will be very, very, very unproductive, right? To work on these equipments. So I don't know if you guys, Dave, if you guys get involved in arc flash analysis and recommendation. I'm sure you do, guys, because you do every system almost now have to do it. So just keep in mind, as the categories goes higher, the maintenance of your system energized will be much higher. And I want to remind you very quick, because we do OSHA training through 70E, makes it the 70E. It's the exception to work on energized equipment, not the rule. The rule is you lock out, tag out procedure. You lock your equipment, you tag it, and you work on it de-energized. You put it in a safe working condition. And then you work on it. The exception, and there are 2 exceptions. Exception number 1F, the troubleshooting, you have to troubleshoot the system energized. You have a problem and you need to troubleshoot. You can't troubleshoot dead circuit, right? So that's one exception. Second exception, if the process depends on, the process is very important, as in you're in the operating room in the hospital. Do you really want to go shut down the switch gear when you work on it, when you image it, thermal image it? Do you? I mean, it would be nice if you can schedule it, but these are exceptions. Or you have a chemical plant, you can't shut the chemical plant because you create a lot of reactions, nuclear plant. So you have to work on the equipment energized. When I say work, guys, you could be changing fuses or adjusting circuit breakers or thermal imaging these equipment and so forth. Any comments, guys? Any questions about that? Comments? Any questions? So that's why short circuit and the interrupting rating of your circuit breaker will decide what category PPE from 0 all the way to 4 that your personnel in the field will be wearing to maintain the system for 50 years from now, right? Expected 40 to 50 years is expected life of a system that we design. So when you design it today, hopefully, you know, keep this in mind that this is what you need to to work on it. I'll talk about this one, guys, the arc flash boundaries when we reach them. Here's my categories. Should have put them in a better, so that's how their sizes. They're still big people. Electricians eat good. Um, okay, coordinated overcome detection device. Coordinated overcome detection device that will leave us, guys, into coordinated and selective coordination. The NEC code book said selective coordination. So hospital is one of good examples of where selective coordination is required. And a couple of other places where if you work in a process and you don't want to interrupt the process, you have to do selective coordination. Because you don't want to maintenance electrician working on the balance of this 277 and 120 fixture trip the main panel, right? And interrupt the process, the whole plant. That's the requirement. Of course, every engineering project that I was involved in requires by the owner selective coordination. You guys do it all the time when you do for, it's kind of a package, you provide it. Okay, so bottom line, if you have a short circuit in one area, it will interrupt and isolate that particular area and maintains the integrity of the power system. So it would not interrupt the power system. So we have, that's your interruption. Here's two examples, guys. I thought non-selective coordination, and these I don't like to look at them being an engineer because we like to look at the graphic. It makes you appreciate the graphic because the graphics clearly, if they're touching each other, you have miscoordination. If they're not touching each other for the most part, you don't have. So that will talk about the speed, how because this circuit breaker here, look at the speed, it's very fast, a quarter to a cycle. Start checking a quarter to a cycle, so very fast, the same speed as the downstream. It makes these 20 amp circuit breaker trip the main if the short circuit is high enough. So here's an example where I have a 10,000 10 times. That's a big, when you have a 10 multiplier as a short circuit, 10 times 20 will give you 200 amp. 200 amp a short circuit will basically will trip both the short circuit, the main, which is 100 amp, as well as a circuit breaker, because if you look at the speed, both of them are very fast acting speeds. And I don't like, again, to look at them. Look at the way they did it here. What they did, they slowed down that guy a little bit. You slow that down that guy from 7 to 20 seconds at that range, versus that will continue to pick up very fast from unlatching to completely interrupting. And by slowing down the upstream, it will give enough time for the downstream circuit breaker to interrupt the circuit if it's within its rating. Any comments, guys? Any questions? Questions about that one? I know we use SKM with the curves is much better than that. This piece is borrowed basically from SPD, and that will give you. I always have been told, guys, if your main is twice as much as the largest branch circuit in the panel, you're almost always guaranteed coordination. If your main is twice, so if the largest circuit breaker is 50 amps and your panel is 100. And circuit breaker at the same time, you have a good coordination. The problem is if you have a main of 70 in 100 amp. Now that becomes a big deal. So if you look at these, are 2 to 1. Most of these are for fuses, of course, different type of fuses, coordination with each other. A lot of them 2 to 1 if they're the same. They go though, and some of them even less than that. Look at that coordination, 1.5 to 1, meaning the main is twice or 1.5 more than the largest downstream. So I thought if you're doing fuses, do you guys have a copy of this there? Do you have somewhere? May I ask? I mean, do you? So it's these are all because you don't use fuses. Yeah. The challenge that I have is when we do the electrical contracts, because a lot of them don't have SKM. You're absolutely right. If you have SKM, you can always look at any fuse that you want, any curve with it. So this. Four to one. As a, and, yeah, 4 to 1. You go higher than that. Yeah. Yeah. I mean, you barely, if you have, I mean, most of the panels I use, yeah, 225 amp panels, and a lighting and receptacle panel, 225 amp, you barely can use, most of it is 20 amp anyway, right? 20 amp, maybe 30 amp, some equipment, a typical lighting and receptacle panel. Like,
Besides the hospitals that you mentioned, that we need to make sure that one that gets us, we don't do a lot of hospitals, but for some, but if you have more than one elevator on a common feed, you have to
coordinate them, yeah, elevators.
Elevator protection devices against the one serving the feeder for keeping that water.
So the
That can be a little challenge.
so coordinating for the emergency system, that part of requirement for any emergency system, any,
If you feed
yeah,
more than one elevator off of one feeder, you know, we got a 400 amp breaker, 400 amp wire goes out to where the elevators are, and then you have two 200 amp breakers at the machine rooms. Those two breakers for 200 got to be properly coordinated with the 400 to prevent one elevator
from tripping.
out the other elevator.
Okay, the rest of them, yeah.
That is a requirement.
Okay.
So the easy thing to do is have two separate 200 amp feeds to your two elevators, then you don't have to worry about it. But as soon as you have one feed that goes to serve more than one elevator, you have to set it.
Okay.
A lot of people miss that requirement. It is a requirement, regardless of what your occupancy is, hospital, whatever, that box any facility.
Okay.
You know, I've done 3 elevators.
Is that building code or like NEC? In fact, NEC says if it's emergency, no? Okay. NEC. Okay. So that's for the fuses.
It can be really hard to coordinate. So, in many cases, the easy thing to do is to have separate feeders for each elevator.
Directly from the main panel,
Yep.
instead of tapping one feeder to feed multiple.
So the more elevators you have, the easier it gets, because the individual overcurrent protecting devices for each elevator is getting smaller
Relative to the main.
breaker you use to serve the feeder. But if you
Yeah.
have 2 or 3 elevators, it can get really hard.
Yeah. So I don't know if you don't use current limiting fuses. You said you don't, not a whole lot of current limiting fuses. Um, I've been in situations where people swear with them. I mean, that's a good example of application. You guys are familiar with it. So if I have 100 amp current limiting fuse right here, and the available short circuit right into my plant is 40, and you go all the way up until it crosses here, and then you go down until you cross this curve and flip it down. So can you imagine? Now I can put, you said you guys don't do that because a lot of liability issues. Now I have a VFD downstream that's below this 100 amp fuse that does not have to be rated for more than, withstand rating for more than 4.6 kiloamp. So that's kind of the whole advantage that I hear that people use them, is to protect equipment, especially power electronics. We have power electronics means a lot of things. So you can, what you end up doing, if you, here's you continue with your circuit breaker coming in here, and down here you will have a fuse or a fuse right next to the equipment, and that fuse inside the controller itself will be sized appropriately to protect your VFD. VFD either right in here, based on the withstand capability of the VFD. So that's a good example of, now this is the RMS value. That's the one that's going to bake your building. The one that's going to shake your building is the I squared, what they call it, the I squared. So that's the magnetic force that's going to shake your building, goes all the way up. That's how they do it. It will knock this one also down. So the shaking, the baking was knocked from 40 to 4.6, and the shaking is knocked down from 92K to 10.4K, meaning you'll have less shaking and less baking of your electronic equipment. So that's where those guys they always
The lesson I learned from Mr. Brumlich in Phoenix is that some of those fuse families have that curve published for a 40,000 amp max, and some of them, and they have another curve for 30,000 and another one 20,000, another one for 10,000, and you have to go through all the curves because it's possible that the 20,000 amp maximum fault current curve for that same fuse lets through more energy than the 40,000 amp curve does. So you have to get all of the fuse let-through curves for that fuse and analyze each one of them in the worst case, because he proves to me that less a fault current lower than the maximum could let through more fault current.
Seems counterintuitive, doesn't it?
Yeah.
Well, the shape of the curve and the angle that intercepting line there and all that stuff. It's possibly. I kept it for many years. If you put 40,000 amps into a fuse, you got 4,600 out, and if you put 30,000 in, you got 5,000 out.
Yeah. So
I suppose
the curve.
the higher fault current causes the fuse to blow faster.
Yeah.
So that's actually less.
So the curve.
That's the fear that got put into me.
Yeah.
And another thing is that they will say, you have to, essentially, they don't allow you to just submit the curve and say, this is what we did. They want you to stamp and sign that as a PD right on that curve and basically take responsibility for the performance of that fuse, which gets scary.
I hear you. Especially current limiting.
Cases where there's a very high fault current, your typical utilization equipment is rated at 5,000 amps. It doesn't have a rating labeled on a tire that it's 5,000 amps. And so, if you got 4,600 through, it's fine. But if you had, if you didn't count on that fuse, or you didn't follow Mr. Brumwich's guidance and some other value led through more than 5,000 during violation. So the coward's way out, the live coward's way out is to do something else. Like on large facilities, you put in a one-to-one transformer, knock your full current down by at least half.
Impedance, yeah.
The impedance of the transformer and solve that.
Okay. The challenge that became in 2011, especially because now if you guys do manufacturing, if you have a bus duct, in 2011 they said if you're to tying a machine to this existing bus duct, the machine interrupting or withstand rating must be higher than the available short circuit in the bus duct. So now you buy a machine from China, and I've been in classes where people in manufacturing, they say, well, I bought this machine from Europe and it says it's rated for 6K. And my system said 25K, what am I going to do? That's exactly how you're going to tie this machine to this existing system. And then my personal answer, I said I wouldn't put my name on it, but I would say the only thing you have other than transformer that knock it down for that machine is current limiting fuse, and make sure you engaged. And from the technical papers I read, and from those guys, again, those guys make it, so they're kind of biased. As long as you don't have overcurrent protection devices downstream inside the machine, that current limiting fuses should be okay. As long as the machine itself does not have overcurrent protection device inside, if it's all no overcurrent protection, no fuse, nothing on the controller side or on the power side. But you're right, that's a big issue.
There's a reason why SKM Power Tools ignores the effects of current limiting fuses.
Yeah.
It doesn't do anything. You put a current limiting fuse in Power Tools, and it doesn't affect the fault current at all. And the senior engineer out there, his name is Johnny Ma.
Yeah.
I met Johnny Ma one time, and I spoke to him many times. SKM is a great company because they will help you figure out what's wrong.
Yeah.
And, so I asked him that one time. He said, we're not thinking about that on here.
Yeah.
Too many variables and current limiting fuses. So I said, I put this out. How come it doesn't change my fault current? He goes, well, we're not going to do that.
Yeah. The fault current itself is calculated assuming there is no overcurrent protection device in the system. It's only the impedance. But the arc flash, though, will take this into consideration. When you do your arc flash, I believe this will take this into consideration, the arc flash studies and the labels. But the short circuit would not. So we'll get into that one. So here's a couple of examples, guys, of current limiting fuses. I thought here's the lit through that you said. Supposedly, and I mean, I'm like you guys, study all the time, and the current limiting fuses, they interrupt in a quarter of a cycle versus a circuit breaker is rated to interrupt in 3 cycles. So 1, 2, 3 within 3 cycles. Could be 1 cycle, 2 cycles, but circuit breaker is within 3 cycles. When you get a fuse that fast that can interrupt within a quarter of a cycle, that chunk of energy here that's supposed to shake and bake your equipment is much lower, and that's how your VFD or soft start supposedly will survive a short circuit condition or a gun fault condition. And you'll see this one all the time. I'm going to get into that one. Here's a couple of examples. I don't know if I'm going to go for this one. I copied it for you guys. This is, I thought, very interesting. Back to type 1 and type 2 protection. I don't expect you guys to read this one, but if you would like, I can PDF this one. There's a PDF, you can get it. They talk about type 1 and type 2 protection. Type 1, basically minimum damage to the equipment. That's exactly what the NEC code requirement. Minimum damage to the equipment if you have a short circuit condition. You know, you might have to change the circuit breaker or adjust certain things, but nothing will burn. Minimum damage. Type 2, no damage whatsoever to your equipment. If you have an overcurrent protection device, if you use a circuit breaker, and you have a type 2 protection, meaning you just literally change a fuse to a fuse or a circuit breaker, flip it, and off it goes. So when you get into the type 2 protection, especially in a higher short circuit, that you almost have to go to a type 2 protection, you almost have to go to a fuse. I don't know if you guys have seen these curves. I thought this is really unique, especially the last curve here. Again, I want to warn you, this is done by manufacturer of fuses, so it makes the fuse look nice. So the bottom one here, it's supposed to give you a lot of protection. So you can see all yes for all this type of protection. So it will protect. So would it protect my conductor? Yes. Would it protect my motor? Yes. Would it protect my contactor or VFD? Yes. So meaning if you put, this is where current limit fuse become a big deal. If you have a current limit fuses on the equipment, supposedly it will provide a complete full protection and overload backup for that particular machine. So that's, I thought, versus if we have, they're comparing different type of fuses with circuit breaker here. So these are the type of the protection that suppose current limit fuses will provide versus other types. Again, we're talking about IEC tool, IEC starter protection. I don't know if you guys use a lot of IECs or NEMA, most of the stuff that we use. But when you go to a manufacturing, especially now, a lot of manufacturing bring a lot of IEC stuff from Europe, contactors and so forth. So you might encounter a type 2 protection that requires you to limit the energy, the lit-through energy, and the only way you can do it is current limiting fuses. Current limiting fuses. Any comments, guys? Any questions? Comments? I will talk about, I left this one until the end. These are the tab rules. Do you guys use tabs? We just talked about the tab rules when you have an elevator. Here's a good example. When you brought your elevator, you bring a feeder. Here's my 600 amp feeder, and I'm just going to tab into what you have done. Here's elevator 1, here's elevator 2, and here's elevator 3 right in the elevator room, and here's I don't know, an elevator 4 here. Now that's these are all 4 elevators fit from one feeder. Do you use something like this through a gutter? I know as engineers we love to use buildings, we love to use panels, because panels are great. Everyone branch circuit directly from a panel. But I've been a lot of design build guys, they can do the things cheaper by utilizing requirement from the NEC code book. Or permissions from an NEC book. That permission is called the 10-foot rule and the 25-foot rule. May I ask, do you guys use this? Dave, do you use the 10-foot rule, the 25-foot rule? So the 10-foot rule says as long as you're, here you go, as long as you're 10 feet away from the feeder or less, you can, this part of the conductor, the 10 feet that you tab from the gutter, does not have to be protected for overcurrent protection device. So what would that save you? It will save you a panel. So that gutter that's full of feeders and tabbed into it, it will save you basically, each one of these is tapped from the same feeder, size appropriately. Instead of having 1, 2, 3, 4 fuse disconnect plus the main, 5 of them in one panel, and I have just one fuse disconnect on the wall and tap from it and cheaper equipment. So a couple of rules for it. Of course, you can't go higher than 10 feet. The load at the bottom here, when you add your load, cannot be more than the overcome protection device 60, then this cannot be more than 60 amps as a load. And then the overcome protection device, the conductor here, cannot have to be 1/10. This is the rule, the major rule, 1/10 of the main, which is 600, and that's where they came up with the equal 60, right? Can you see that? 1/10 of 600 is 60. And then the amp rating, the load cannot exceed what the conductor is rated for. This is interesting. The next standard rating that we talked about a minute ago, not required. So now this is where your conductor have to match your overcome protection device. You can't go to the next standard up that we just talked about when you're doing tab rules, the tab rules. And shall be raceway in a raceway. So you have to protect the physical protection. Typically, we put them in a raceway. The 25 is exactly the same, except 1/3. So what they do is they take 1/3 of the feeder, which is 1/3 times 600. They give you the 200. 1/3 times 600, they'll give you the size of 200. So the smallest cable that I can tap up to 25 feet away from where the gutter is located, 25 feet, in this case, because of the 600 amp main, is 200 amp. So you go to the table and you size yourself a 200 amp conductor. It can't be 190, can't be 180. It has to be exactly 200. So you can't go to the next standard up. The same thing here. If it's 60 amp, then my conductor here cannot be less than 60 amp. So you go to the table based on the lugs. Most of the time, these are 75-degree rated lugs because it's 3-phase. When we tap, a lot of these are 3-phase. So if you have a 3-phase load, 99.9% of the time you're talking about lugs rated for 75. So you go to the 75-degree column and size yourself a conductor that can carry 60 amps or more. I thought this is really interesting, tab rules. I do have a couple of tab rules, guys. I will go over when we do the transformers. I don't know if your primary, secondary protection for transformers and primary only protection. I have a couple of rules that go related to the tabs when we do the class about transformers and transformer protection. Any comments about the tabs? Any comments? What's the advantage of it? Cheaper equipment. Disadvantages, you don't have localization of all your overcome protection devices in one panel. So you have a gutter and you have a big, in this case, 600 amp, probably 2 sets of, I don't know, 300 kcm going into a gutter, and you're tapping from each one of these phases and going everywhere. What's the disadvantage of it? Survivability of the system. Now, if something to happen to this cable here, you lost every single elevator on this feeder. And like Dave said, if it's elevator, you have to do coordination between each and every one of overcome protection device and the main overcome protection device. Is that what you meant by the feeder, Dave? When you take a feeder and you feed multiple of them from a panel? It doesn't have to be like this way. It could be another panel too.
Well, it doesn't even have to be tapped. You can have a separate overcurrent protection device on that feeder for each other.
Yep. The same size.
Yeah. You have to coordinate the overcurrent protection device.
Yeah. Any comments, guys, about the tabs? So these are what I thought the tab rules. Disregard that one. I wanted to. So this is the stuff that you guys. A couple of coordination and a couple of things. I thought if you're green and I personally use it with a lot of question marks being I like circuit breaker like you do. You can utilize them a lot. But if you want to understand a lot about how single phasing and all this stuff, this is really a good document to read. Get you a lot of understanding of short circuit. I couldn't find other than IEEE, this guy, if you guys want to sleep one night. Here's how protection and coordination of industrial and commercial power system. That's the latest and the greatest IEEE book that all the SKM is based on. So do you belong to the library of IEEE? So you can, these are all PDF too. So it's they're interesting, put it this way. So okay, so let me go on that one here. I wanted to walk you very quick.
I just wanted to see what year it was.
I got it. Okay, so here's the article that talks about overcome protection device. I wanted to. Do you guys use supervised industrial installation? That's industrial only. They relax the rules if you have a manufacturing floor and you're using 25 and it's powered with a 2.5 megavolt amp. The size, that's a substantial size, small city size. How much? So that's, I thought, just be aware if you're doing supervised industrial, you're going to have a lot of protection. I want to bring to your attention, guys, the overcome protection device. There's a lot of exception. These are all the other articles that will, remember the 1.25 that we talked about and we're happy with? There are other places like AC equipment and motors and busways and capacitors, which we'll be talking about class 1 and 2 circuits, where the rules to size overcome protection device are different. So make sure if you are doing with welder or a fire pump, for example, and you do an overcome protection device, it doesn't, you have to go to the article because it modifies what's in 240. I always like to bring the small conductor rule guy here. You don't use a lot of class 2 and class 3 circuits there, do you? Class 2 control circuits, do you guys get involved in that? If you don't use class 2 and class 3 circuit, then you start at number 12. So if you have a number 14, I don't think you guys even specify number 14. Nobody, no engineering firm, that's baby stuff. Contractors get mad when I say that because it's cheaper, Chad. Number 12 or lower. So if you have a number 12 aluminum or, okay, this is where it starts. You don't use aluminum. You choose number 12 copper 20 amps. So this just tells you if you're using number 12 conductor, you cannot break the number 12 conductor with more than 20 amps, with a few exceptions when it comes to motors. The exception is when it comes to motors. So that's very, very important rule. So you have a lighting circuit, 20 amp. You can't put a 30 amp circuit breaker on a 20 amp circuit, on a number 12 circuit. Number 10 conductor is rated, number 10 copper, we're talking about copper here, is 30. So if I decided to pull a 30 amp lighting circuits and use the tab rules and tab that 30 amp, do you guys use 30 amp, Dave? Do you use 30 amp or everything is 20? A lot of people use 20. Sometimes you use a 30 amp lighting circuit with number 10 and you take it somewhere else and right in the panel you tab with number 12 to the fixtures. And that will give you, so that would be site oriented. Site a lot of places we go. So that number 10. So, but what I bring to attention is 12 goes with 20, and 10 goes with 30. Another thing that I thought very interesting is right in here. These are all the standard overcome protection devices in NEC code book 240.6. I'm sure it's a review for all of you. A few people don't understand that this is adjustable trip circuit breakers. It's unlimited amount of sizes. So if I have an adjustable circuit breaker, these I can go between 30, like for example 25, 250 to 300. There is no size here. Though if you have an adjustable circuit breaker, you can trip between 250 and 300. So and where would that be? Adjustable trip circuit breakers, you can go based on a long time pickup. I'll show you the examples that we did, but this is very, very handy. This is where it tells you restricted access adjustable trip. So you have an adjustable circuit breaker. The last thing you're going to do, an electrician who doesn't know anything, you go to that panel and start adjusting the long time pickup on this circuit breaker. Now this circuit breaker, literally with a flip like this, you turn the circuit breaker from 2000 amp into 3000 amp just by flipping it this way. The capability of the circuit breaker, and you guys are very familiar with adjustable circuit breakers. So they have to be restricted access to them. So that's why we put them behind panels or closed doors and so forth. This is my favorite, but you guys don't use it. Fixture wire, you can tab. So if you have a 30 amp circuit, I can use number 14 conductor inside the panel and tab a 30 amp circuit, feed multiple system. If I have a 40 amp, see, you are pulling a 40 amp lighting circuit, a 50 amp lighting circuit with number 8. You can take it all the way to the panels and use number 12. A lot of people guys use 20 amp, number 12 easy. The advantage of using 20 amp number 12 is you don't put all your eggs in one basket. If you have a 50 amp lighting circuit, 3-phase, you can put the whole probably 2-3 stores in this building on one 50 amp, 3-phase, 277, 480 lighting circuit, wouldn't you? I mean, if you have 50 amps, a lot of juice at 480-277 for lighting. So, but I thought these are really cool. You can, a lot of people take advantage of them and make a system a little bit more unique. So ground fault protection, I'll talk about ground fault protection. This becomes also a very big deal. The NDC code book require you, with 3 exceptions, if your circuit breaker is very big, meaning 1000 amp or higher, and if your system is 480, 277 or 600, you must provide on the feeders or the brand circuits ground fault protection, specialize in looking at the ground fault. At the 1000 amp or higher level, the ground fault become high enough that become destructive, burn equipment, but low enough that cannot be sensed by the CTs on the phases. So they require you to provide 1 protection. 3 exception, continuous, you're cooking nuke in your building. You don't want to interrupt this one because of a ground fault. And the other one is the ground fault is provided somewhere else in the system. And of course the fire pump. If you have a fire in your building, do you care if you have a ground fault sitting in your building? The building is already on fire. No, that has not changed in 2011.
I want to say that there's one that says that it needs to be 1,000 amps or more, and at least 6 feet in length.
6 feet in length?
Over 6 feet.
No, it's the ground fault. I think you're missing. You're talking about axis, electrical axis. Electrical axis 1200 amp actually, 1200 amp and 6 feet or more. You're required to put 1 door here and 1 door here, with a couple of exceptions. That's the ground fault. So I thought that's really interesting in the NEC code book. You guys don't care too much about some of the tab rules here. I found them very interesting because contractors love them. 240.21. So I picked 2 tabs from here, guys, and I'm going to pick a couple of others with a transformer here when we talk about transformers and just monkey around them. I thought they're really unique and unique. I think they're unique. So ground fault, I want to have. This just talks about the circuit breakers. There's one thing I want to mention before I go. Supervising electrical. Here's a series rated that we talked about, goals selected under engineering supervision, all the stuff that we said, tested by the factory. This one is very interesting, came in 2011, non-instantaneous trip circuit breakers. You guys are familiar with that one. It came as a change. If you have a circuit breaker that you disable the instantaneous on it, you are required by code to do one of the following: zone selective interlocking, differential relays, or energy reduction maintenance. Zone selective interlocking, they look at circuit breakers ahead of the main and out of the main, and they're looking at that zone. If there is a short circuit inside the switchgear, they use them a lot in high voltage. That zone selective interlocking will bypass the delay or the interruption of the instantaneous, and will instantaneously trip the circuit breaker to prevent from a huge damage that could happen to the circuit breaker, as well as to the people who are working on that circuit breaker energized. Differential relays, I believe it's also the same thing when you have you're measuring the power in and power out. Have you seen them, Dave? Any of these differential relays on low voltage and high voltage? You use them all the time. So they're looking at what comes in and what comes out, and if what comes into the switchgear, what comes out of the switchgear and all the feeders. If there's substantial difference, you have a ground fault or a short circuit inside the switchgear, and will instantaneously trip to limit the arc flash and arc blast energy. All this came to reduce the amount of arc blast that you can do here. The last one is a lot common: energy reduction maintenance. You have a switch, square D, and all of them have it. If you're working on that switchgear 4000 amp energized, and you put your PPE, you go there and you turn that switch on. Basically you enable the instantaneous and screw up the coordination. When you're enabling the instantaneous means screw up the coordination that you've done. No problem, because I'm working on it. So screw up the coordination, enable the instantaneous. What's the advantage of that one? Now I have a proper PPE that I can work on energized on this piece of equipment. So did you guys do any of this? The energy reduction switch and so forth? So that came in 2011. If you work on supervised industrial location, this is kind of, I thought it was weird. They allow you to size, if you have a 4000 amp switchgear, they allow you to size a conductor based on 95% of it. Remember the 800? 800 or more, you have to match. You have to match the circuit breaker. If you're in supervised industrial location, you have 1,000 amp circuit breaker. You can size your conductor for 950, and the code is okay as long as supervised. The idea, guys, is they're smart electricians and maintenance people working on it, and it becomes, the protection becomes, if we have a short circuit protection on it based on curves, the full load rating is not a big deal. So the last one I'm going to do on these is, do you guys do over 600 volt? Over 600 volt, the way they do the over 600 volt to protect the conductors, this is really interesting. Rating or setting of overcurrent protection device. So suppose I have a medium voltage 13.8 feeder and I need to size the overcurrent protection device. Very clear. If you read through that one, it says the long time pickup element setting of the breaker or the trip setting of the electronically fused shall not be more than 6 times the ambiguity of the conductor. So I have a medium voltage cable 100 amp and I want to protect it. The long time pickup, I can make my circuit breaker 600 amp long time pickup, not short circuit, not ground fault. So long time or a relay, I can set my relay 600 amp to protect a 100 amp circuit breaker if my system is 5k kilovolt or 50 kilovolt, higher than 600 volt. If it's a fuse, for the fuse, we have 6 times capacity of the conductor, whereas the fuse shall not exceed 6 times. Circuit breaker is 1. The circuit breaker shall not, of the breakers, one of them is 3, one of 3, I'm sorry. So the continuous amp rating of the fuse, if it's a fuse, it's 3. If it's circuit breakers, is, so I can have a 300 amp rated long time pickup fuse on a 100 amp medium voltage feeder, or 600 amp long time pickup circuit breaker on 100 amp circuit breaker, 100 amp medium voltage cable. I don't know if you guys size these. I found it very interesting because it's against everything that we know in the low voltage. Since when you put a 300 amp long time pickup on a 100 amp feeder, probably the exception for this is when you deal with motors, we do something like this. But 600 amp circuit breaker long time pickup on a 100 amp feeder, unheard of in the low voltage industry. I can't think of a place where you do that long time pickup, even with motors. Do you guys think of any place? So I thought this is really interesting to do. Okay, I have 15 minutes. I'm going to move you directly into SKM. Okay, so where am I here? Do what? I'm sorry, what? Because you always size them. Because we're protecting them from short circuit, our main intention in the high voltage. There you go, thank you. Okay, so my understanding is because when it comes to the medium voltage, the full load current is really the least of your issues. Okay, here's the power system. I'm sure you guys, this is just showing the short circuit available coming into the building. I assumed it's 80,000 amps coming in. Half of it is switch gear. You get these two numbers from Excel, right? These are what the contribution of Excel. Then you can see the block here. My switch gear right now is sitting at 75K. So I have to rate this piece of equipment as I have to rate it as 85,000 interrupting rating. Okay. So you build your system. I'm not going to go through how to build the system, but I thought. I'm going to go directly into the curves. So this is what you call, if you dealt with it, this is the one-line diagram. In order to analyze the system, you have to build the one-line diagram and model it, build everything inside it. I'm running this short circuit without the generator. If you run them with the generator, you will exceed the capability. I don't know how you guys handled it. In some projects that I was involved in, we run them without the generator, and then we write that if you are to run the generator in parallel with the switch gear, you will exceed the capability of your switch gear. So, and typically now you cannot run in parallel, right? You can't run except momentarily to just switch yourself off the grid. Otherwise, you're going to be in the business of production. And there's a lot of EPA requirement now that prohibits you from running your generators to produce power, right? So we use them as backup system emergency. So Anyway, so that's your riser. The color, the red means these you cannot work on these switch gears energized, and orange means you can, and that's how you can do it with Excel. I don't know if you guys do that graphically. You can represent a lot of stuff in your graphic. So anything red, meaning based on my arc flash calculation, I cannot do it. So I'm going to go very quick here. So when you run balance, and then here's your demand, load flow, short circuit, load calculation, you run BAM, and you get all your calculation up and running. You guys have done that, and it updates all the calculation they've done. Arc flash, I'm going to go directly to my arc flash. So here's the arc flash based on this book. Do you guys run your arc flash based on other than this book? You can have the option of running it based on NXD7, IEEE 1584 is the most common one. I don't have it with me. Or you can run based on National Electric Safety Code 2014. Do you run any of these based on it? You've done that? Okay, so you've done based on 1584. Okay, so that's what the most common one, the default, and then you run your calculation. You end up with all this. You can have work permit here. There's a lot of stuff here, really cool. The PPE table, but the most important one is the customer labels. And review my customer labels. Here's all my oh, that's why I want to click. All these are my buses. When you build your power system, the way I learned how to do it is you B for bus, and C, there's every company has its own acronyms. So when you're looking, every time you see a B, this is an actual piece of equipment that I'm interested in knowing what the available short circuit as well as arc flash right on this piece of equipment. So if you go continuous here and you got yourself what you guys are looking at, I'm going to focus directly onto the red. So I have this piece of equipment is the CT cabinet, and if you guys remember the CT cabinet, my CT cabinet was I bring my cables into the CT cabinet. So to work on this, look at the flash hazard boundaries, 41 feet, because there is no fuse, current limit fuse or non-current fuse between the CT cabinet and the transformer that I know of. The flash hazard, look at that flash hazard, 282 calories per centimeter squared. That's there is no category. They go as high as 40. At least based on PPE. The PPE does not exist. So this is the most important thing, the arc flash, arc blast, the arc flash. Right underneath is what we call it the shock hazard. The shock hazard is easy in terms of don't stick your hand there and don't touch anything energized. So if you put gloves 00 because they're 600 volt rated, you're not going to be shocked. And limited approach, you guys are familiar with limited approach. That's from the NE Secret book clearances. These are the clearances from the NE Secret book. 3.5 feet in front of the switch gear based on condition. This is condition 2, I believe, which is grounded object in front of you. Restricted approach, that's you in your PPE working on the equipment. Nobody can enter the restricted approach while you're working on it. 1 foot. Prohibited approach, that's the tip of your screwdriver in and as you torque, or the tip of your tool as you torque these lugs energized. This is for working energized. Again, the rule is de-energize first. I'm laughing because there's a lot of issues could happen. So when you want to torque your equipment, you want to work on them de-energized. But if you were to work on them energized, these are so-called the shock hazard, and right above them is the arc flash hazard. So you can see there's nothing here. I'm going to go to bus duct. I have a bus duct of 480. Actually, this should be 480. My bus duct of 480, I have 9-inch flash hazard. It's 0.41 category, PPE, non-melting or non-treated fiber, so that will be class 0. And why? But look at the voltage though. You guys see the voltage? It's a 208 volt system. The reason why this is negligible, it's a 208 volt system, and you can remember the 208 volt system, the arc flash is really substantially different. The shock hazard continue to be the same. So look at the shock hazard, just don't touch at the 208. At the 480, the electrician will tell you that it comes and grabs you at the 480, right? So don't touch and restricted approach and prohibited approach. At the 480, don't even get closer than 1 foot unless you are in the gear, the PPE gear. So that's another one. I'm interested in the chiller. So you guys work with mechanical engineers all the time. So right at the chiller itself, Now that's with the VFD is going to be sitting right there. Somebody's going to be troubleshooting inside the VFD. It's nice to know what the arc flash right there. So I have again PPE arc flash shirt and pants, and it's a 6.9. That will be category 1 if I remember right. And this is the label that you need to do, of course. The PPE level, as well as the labels. The arc flash is 4 feet 5 inches. That's the boundary that you have to restrict the approach to it as you work with your equipment. I'm going to go to the generator. I'm not running my generators here, but I don't have a main for the generator. My main is right inside the switch gear. That's why the generator is really that high, because they don't have a main circuit breaker to limit the energy. So like I said, Dave, when it comes to the arc flash, if you don't have a circuit breaker, it will make or a breaker or a fuse. It doesn't matter, current limiting or not current limiting, it will make a substantial difference in the amount of arc, because it's based on the time and the interrupting time. But for the short circuit, it doesn't matter. Your short circuit calculation can be done without putting a single circuit breaker in your system, a single circuit breaker. Any comments, guys, about these? Any comments? Any question? You guys do this all the time, and then you send them to make your labels for your equipment. I'm gonna
That's the hard part.
the proper label. $8,000 to wow. Yeah. Interesting. I'm gonna go, guys. Here's the arc flash. When it comes to the overcurrent protection devices, the single most important thing after you size them properly for safety is the survivability of the system. The worst thing that could happen to you is you walk into a building, a short circuit on a light, trip the main. That's a bad day for us as engineers and everybody else. So here's a 3 that I ran. I'm going to go directly into the air. This is a chiller, just directly to a chiller coordination. Feel free to jump in, guys. So I have my main at the top right here. I disabled the instantaneous on my main, assuming you can see my main instantaneous. I'm going to go to the settings. Here's the settings. This is Magnum DS 480 4000 amp color hammer switchgear circuit breaker, rated for 85K kilo amp interrupting rating, and that's all the families that you can get from them. The sensor is the CTs that you can get. They're rated for either 32 or 4, and the plug, you can plug these only at, if you put a sensor of 4, you can only plug it at 4. Then you get into long time LTPU, long time pickup, long time delay, short time pickup, short time delay. Long time pickup is the how much can you pull continuously. These are 100% rated circuit breakers. So if you put one here, you literally can pull 4,000 amp out of this circuit breaker continuously. Then the long time pickup is the single most important contributor to the arc flash. Long time pickup right at the bottom, long time pickup, and the delay for the short time delay. This area right here is the area that contribute a lot to your short circuit to arc flash. So this is sitting at 20 seconds here, and this one is sitting right now at 10 times the long time pickup. 8, which is 8 times 4, 32,000, sitting at short time pickup. That's your short circuit that contribute to the arc flash. And then short time delay, I'm delaying my instantaneous, my short time pickup 0.5 of a second, which is eternity in the life of a circuit breaker. Your equipment, if it's not rated for this, it will completely burn. Unless you have a drought arc switch gear, you would not be able to delay this one as much as I did here. Okay, so that's the reason why we did that when we disabled the instantaneous. That's when the code require now is to have that maintenance switch where the maintenance switch will drop this leg down. I don't know if I can all the way. Now I'm disabling it. I can drop it all the way down to the bottom. If I bring my instantaneous, here's my instantaneous leg here, it will drop it down all the way to the bottom here. So, and that's either you do that or you have the function, delete the segment here, or you have the maintenance switch. So then I went to my generator because my generator is also there. If I run on gen, I want the gen to be set almost like a main. and then I coordinated my chiller overcome protection device. This is my chiller, and I have an 800 amp set at 1, and I can adjust my setup over my chiller. For chiller, guys, here's my starting curve for my chiller. Again, you can talk to the based on the start curve, and this is starting time of 10 seconds assumed, and information about this chiller that you can get from the manufacturer unless you have it. And then is my chiller, all the information about it. So that's my starting curve for my chiller. It's 10 seconds at 6 times, I believe, full load current. Now what you need to do, this, as you know, I know you guys know that, the ones who do it, you need this one to clear the starting curve. Now if I put it this way, every time you start my chiller, unless you have VFD on it, unless you have a VFD or soft start on it, which a lot of them do, it will trip. This is across the line, by the way, start. If you to do the across the line, you have to move the instantaneous. So you can see if you have an instantaneous, you can adjust the instantaneous. The further to the right you move the instantaneous, the more arc flash your people who are engaged in working on this equipment energized will be exposed to. So it's not. So this one actually, yeah, that's instantaneous here. I'm setting this one here. See my instantaneous going all the way. Yeah, there's a couple of things that you can adjust. Here's my instantaneous. Here's my short time. I can adjust my short time. I'm moving it all the way up. There's a whole lot of is right over it. Yep, you're absolutely right. So if I move my instantaneous all the way to here, so you need to be as close to the curve, the starting curve, but not overlapping with it. So that's one. I thought the other one is the circuit breaker that has circuit breaker panel, because the same curves are coordinating. Now what I did here, I have my transformer damage curve. You guys are familiar with my transformer damage curve. I have my primary transformer overcome protection device, and my secondary panel circuit breaker, which happened to be a lower grade type. It's an it's a 240 volt HKD 300 amp 100 kilo amp, because it's a 2.8 system, and it's thermal curve. It's not unadjustable. The only thing you can adjust is the instantaneous. You can adjust my instantaneous if you move it this way or this way. That's the only adjustable factor in this. So what you need to do is, my point is, you need here to clear the inrush. The primary of your transformer must clear the inrush. So when you start your transformer, you are not going to trip your circuit breaker on an inrush. But sometimes it's really hard. I don't know if you guys, Dave, if you find it very hard, if you use two different types of circuit breakers, hard to coordinate between the primary of the transformer and the secondary. But who cares? I mean, you do your best on it, because if the primary trips or the secondary trips, the outcome is you lost the receptacle panel. You try to do the best that you can do in terms of coordination between primary and secondary of the transformer. I like to bring to your attention, guys, the damage curve. This is called the damage curve of the conductor. So this is the cable feeding the transformer, and this is the cable feeding the current. Cables have a full load rating as well as withstand rating before smoke start coming out of it. So that will give you, if you look at them, they are to the right of my two circuit breakers here. So I can guarantee, well, I can't guarantee you, but if we're looking at pictures here, if equipment act as it's designed, and if the information updated in SKM based on what I get, then this circuit breaker will not be burned if you have a short circuit or a ground fault in your building. If so, you can see right here the receptacle, this circuit breaker right at this point. If the short circuit is that high, it might damage some of this circuit breaker right in here if it's that high at the bottom. So, but this circuit breaker, the secondary, I know it's the available short circuit stops right here, so it's not going to damage it. The secondary, the primary though, my primary looks like my conductor at this point here will be a race between the circuit breaker tripping and the conductor start heating up, because it's very high short circuit on the primary side and the 480. So that's what I thought. Just a couple of, I know some of you guys don't deal with that, but the most important thing about the overcome protection device is the coordination. So, any comments, any questions? I have 2:31. You told me to stop at 2:30. Any comments? So what I have for you guys on Thursday, I'm going to take motors and we'll do a couple of curves for motors as well as special things about motors and branch circuits and so forth. Thank you.
Chad did a yeoman's job of trying to cover. You go to the extension class at Madison on overcurrent protection and coordination. It's a full 3 days. 2 8-hour days and a 4-hour day.
Yeah.
20 hours to cover.
Yeah.
Just give you half of a session.
Yeah. So the assumption is you guys have seen this to a lot of people. So if you, yeah.
There's a couple people that had a course of these type of rules and those that haven't. Are experts. But we think better than that. There are a couple people that haven't seen it all. So
Yeah. Okay. Thank you.
Thanks, Chad.
Thank you. Thank you. Thank you.